We already know the phase portraits of linear systems, and we also know that nonlinear systems can have kind of combination of several types of the phase portraits of linear systems. Now let's study the next type of the phase portraits, which is appropriate only for nonlinear systems. This is limit cycle. There are three types of the limit cycles, but all three have one common feature: this closed trajectory, which is called a closed orbit. If the system starts on this closed orbit, then it will stay here forever. If it starts somewhere else, inside or outside of the closed orbit, then we have three different cases. The system has a stable limit cycle if it moves closer and closer to the closed orbit. The system has unstable limit cycle when it moves farther and farther from the closed orbit. And system has half stable limit cycle if from outside it moves closer, but from inside it moves farther from the closed orbit, or vice versa. For the example, let's take van der Pol equation. This is dynamical system of the second order that can be represented in the following form. And for its simulation, let's take the following initial conditions and the value of parameter mu. We can look at the behavior of x1 and x2 separately. So we see cycles for x1. And for the x2, we will also see some cycles. And if we combine x1 and x2 versus time, we will see the following. So you see how system behaves for these equations. Theory on limit cycles is very complicated with many details and many cases. But let's take just a small part of it. Assume we have the following differential equation that can be represented in this form or in this form, and suppose that f of x and g of x satisfy the following conditions. First, f of x and g of x are continuously differentiable for all x. G of x is odd function. Also, it is positive for all x positive. F of x is even function. And the following odd function, f capital of x, which is the integral of our f small, has exactly one positive zero at x equals a. Also, our f capital of x is negative on the interval from 0 to a, positive and non-decreasing on the interval x is greater than a, and f capital of x tends to infinity as x tends to infinity. If we satisfy these conditions, then our system has a unique stable limit cycle surrounding the origin in the phase plane. Let's solve the following example. Show that the system has a unique stable limit cycle. Let's check our system for the mentioned conditions. Our g of x is this, and f of x is this. Let's write it down. G of x is x, f of x is 2 times x squared minus 1. First, f of x and g of x, we see that they are the polynomials. And we know that polynomials are continuous and differentiable for all x. Next, if we take g of minus x, this is minus x, and this is the same as minus g of x. So we see our g of x is odd function. Next, g of x, which is x, is greater than 0 if x is greater than 0. Next, let's take f of minus x. This is 2 times minus x squared minus 1, which is the same as the following. And finally, this is the same as our f of x. And we see our f of x is even function. And then the last step, we need to define the function f of x, f capital. This is the integral of our f small. So we have 2 times u squared minus 1 du. And if we continue, we'll have the following: 2u cubed over 3 minus u, and the limits of integration. If u is 0, then the whole expression is 0. If u is x, then we have 2x cubed over 3 minus x, and we can also write it as the following: 2 over 3 x, and then x squared minus 3. This is a cubic parabola, and it looks like this. And we have the following x-intercepts: √3, minus √3, and 0 in the middle. So let's look at this graph. Our positive 0 is √3, so a equals √3. Then we see that between 0 and √3, our function, our cubic parabola, is negative. The next, we see that if our x greater than √3, our f capital is positive. And finally, we see that f of x tends to infinity as x tends to infinity. So all conditions are satisfied, and we can say that the system has a unique stable limit cycle.